I'm José María García Valdecasas. I'm from the Operational Oceanography and Coastal Engineering Division in Nologin. What we do is to provide solutions to increase the knowledge in the ocean. This information we get normally from numerical models or from observations. Where available, we prefer to use the in-situ observation from moorings, fixed buoys, or any other kind of instrument, because this provides more reliable and complete information in that area. But the problem is that normally during severe storms or due to maintenance, we have gaps in the time series of these instruments. So you have to use the information from models or try to provide another data to fill these gaps. In this context, in collaboration with the Spanish agency Puertos del Estado, we did a project to fill the gaps from the fixed buoys with data from models. They have more than 30 fixed buoys along the coastline of Spain. This covers more or less 8,000 kilometers of coast, and they have both deep water buoys and coastal buoys. Normally what we would do is to use the data from the models covering those gaps and do a hybrid time series using in-situ observational data with numerical modeling data. But what we wanted to do is to do a neural network that could provide the best data available coming from the numerical model, but not using the raw data, but some kind of mixed data using wind, waves, and also currents to provide the wave parameters that the buoy has. So for this, we have to choose first the numerical model we are going to use. We chose the CEMEMS EV regional model because this model has a high resolution in the area, and also it covers a multi-year hindcast that is needed to do this gap filling for the time series. For each of the buoys, we have to train one neural network for each wave parameter. We train 3 parameters: wave height, peak period, and mean period. Once you have the neural network trained, you have to achieve the most accurate value. So for this, we decided to go to a bootstrap aggregation technique that doesn't train just one neural network, but trains a number of neural networks, and you use these results combined in an aggregated way. So you get a neural network that gets the best results, but without overfitting the neural network. For example, in the Villano buoy, which is in the northwest part of Spain, in Galicia, we have an increase in the accuracy of nearly 15 to 20% compared with the numerical model of the EUMETSAT. But if we go to the mean period in a place in the state of Gibraltar, we have a buoy in Tarifa, and we got nearly 50% of accuracy increase for that wave parameter. This is because in the state of Gibraltar, the currents are very important, and the multi-year hindcast we used from EV didn't have into account the currents. So when we include the currents in the neural network, we get a more accurate result in this area. We did not just try this neural network, we did also try recurrent neural networks in the long short-term memory neurons for these recurrent networks, and also convolutional neural networks to see if we could get an increase in the accuracy of the neural network using different kinds of neural network which are more difficult to train and more computational cost expensive. The truth is that we didn't have an increase in the accuracy. we did increase with all the neural network, we did increase the accuracy from the model, but we didn't increase the accuracy from the multi-layer perceptron network. And the cost of these neural networks was higher than that with this single or simplest neural network. So we decided to just keep the multi-layer perceptron network and use these results. What we found out after training the network and filling the gaps is that as we are using a numerical model that is in operational from CMEMS, we could use the forecast from this numerical model to provide a more accurate forecast in the location of the buoy. So we could increase the accuracy of the forecast, which could help all the maritime operations and port operations. Normally, port operations depend on the environmental parameters or variables. So if the value goes above a threshold value, they have to stop all the operations. For example, wind speed if they are using cranes, or wave height if it's a vessel that is going into port. So if you give a more accurate prediction, you are going to reduce the risk of these operations when they are planning for a 3 days or 5 days in the future. The main issue we normally have in neural networks is that the more you train the neural network, you can overfit the result, and sometimes you get worse validations. So your prediction can be worse than if you didn't train as much. With this technique, what you do is train several networks, and what you get is a result for each network, and you do just an average of the results. So what the final solution is the best one. You avoid this overfitting or overtraining of the neural network. So it's a way to get better results from this artificial intelligence system. So sometimes it's much better to go just to a more basic neural network. I think that the artificial intelligence and neural network fields are right now in a research position when we are speaking about operational oceanography or coastal engineering. But I think that in the short term, or maybe in the mid-term, we are going to be able to combine the results from numerical models, all the observations from in situ instruments or satellite data with artificial network, and provide more accurate results that we can use to increase the knowledge of the ocean.